SageMaker Training. Hello, it's Nono, and we're just going to see how to train a custom TensorFlow model in SageMaker Training. What I want to go through is first seeing what SageMaker Training is. I've mentioned it before and you already probably know. I'm going to also guide you through how to customize a TensorFlow model script and also train this model in SageMaker. The first thing that I took a look at is the instance types. It's a bit obscure, a bit hard to actually understand what's in there. AWS has 3 different types. I think these are EC2 instances where many of your service will start. So you, for instance, will start an EC2 instance and then AWS just provides you with a notebook that is running there. You can do the same for training or to deploy an instance or for data processing. What they have in terms of SageMaker is general purpose, compute optimized and accelerated computing instances. And there's some that are marked as fast launch. They describe those as the ones that start in under 2 minutes, but I've actually tried them this morning and none of them starts before 2 minutes and a half. They all start at 3 minutes more or less. So you have to wait until the machine switches on and gets started. The ones on there have GPU, they're more expensive. They allow you to run TensorFlow algorithms or PyTorch with GPU and train a lot faster. The ones on the left are cheaper. As you go below, they will get more expensive. One thing to note is that the ML2 and so T2 medium and T3 medium are the cheapest ones that you should use for normal day-to-day notebook if you want to do things on the cloud. And for spinning up training, for instance, or to do things with GPU or to run inference over a large amount of files, you want to use the P3 2x large, 8x large, or 16x large. There are many others. But as you can see, the prices go like 84 times more expensive and above. So the gist of this, what we're going to see today, why it makes sense to see this is because if you use the T2 medium or the T3 medium and just pay 5 or 6 cents an hour, you can spin up training on the more expensive instances just for the time that you need to be training and not for the entire time that you're like preparing your data, your model and visualizing results and things like that. What we're going to see, we're not going to go in depth into this, but just to give a bit of background, this is the Fashion MNIST dataset. This is a dataset of 60,000 training images and 10,000 test images of 28 by 28 pixels of clothing that Zalando, that is a competitor to Amazon, but just shipping clothes for those who don't know what it is. They tried to do this as a drop-in replacement to the original MNIST dataset that I think the team of Jan LeCun put together in the 90s. Something a bit more modern that is not just recognizing characters, but recognizing piece of clothing that are images. One thing to note in this dataset is that it's really well prepared. Like all the images are pre-formatted in the same way. The background is completely black and the alignment is really good. The classification task is easier in that sense. But one thing that I discovered along the way as well is Spotty. I haven't tried it. Spotty instances are EC2 instances that otherwise would be more expensive to train with in low demand times. This tool specifically, what it does is that it tries to make use of those instances to train your in AWS or GCP. What it does is that you can reduce up to 90% the cost of training. If you're going to train a model and you don't care that it happens overnight or in one day or in a few hours, and you're not in a rush, you can just schedule the job. And I think how it works is that it can get an instance when it's cheaper and then train your algorithm there. This is the model we're going to use. It's just like 1 input layer and 3 layers. Is really simple. It trains really fast and we don't even care about the model training properly. It's just like to classify that data set. Now I'm just going to go through the code that we're going to see so we don't just see everything from scratch. This is a Python notebook. Everything is already written there, but I expect that we can maybe copy paste or rewrite to not spend too much time. I don't like usually when a tutorial is just like executing a notebook because that's not really what I want to do. If we can do some coding today, it would be good. So the first thing is to train a custom TensorFlow model. We just have to import the SageMaker library that is available when we open a notebook on SageMaker. And then the datetime, the current timestamp to the name of our job so we can keep track of what was trained when. SageMaker just allows us to get the role and the region that we're currently on, so we don't have to hand code that, and this notebook will work in any region, and also to then later instantiate what's called a TensorFlow Estimator. The hyperparameters of this notebook are the experiment name, so in this case I would ask you to change Nono for your name, so that way when the training is listed on the trainings list and also saved to S3, you can identify which ones are yours. The entry point is any Python file that you can rename, and we'll see what. Epochs, this is a hyperparameter that we input into the estimator. Right now it's set to 1 because what we just want to do is try that the instance is spinning, that the training is happening, and that the model is saved, even if the model doesn't get trained for a lot of epochs. And then the instance type, this is what we mentioned before, that you can either use ML P2 X large, P3 to X large, T3 medium. Some of them have GPU, some of them don't, some of them are faster, some of them are slower. What you can see on the right is this fashion mnist.py. I tried to make a template out of it, so removing the code that we're gonna now have to get from that document that I gave you. And that blue area on the top is one of the to-do things that we have to do. Define the model, compile it, train it, evaluate it, and return it. Then a method that loads the data, a method that parses the arguments of this command line tool that we're creating in Python. And then at the bottom, it's where we actually call the loading data method, the model creation and training method. And then later, if we have a host, we will save the model. In this case, I wrote code to, the comments are changed, but above we're training and saving to a Keras format, to the H5 format, and at the bottom we're saving the save model format. In summary, on the right, that would be our really simple custom TensorFlow model and load data method. This is the other thing that we need to have in mind. The good thing about AWS is that it provides you a way to just change parameters on a URL and obtain an already built Docker image. In this case, we have to get the parameters for the region, for the framework, the type of job that we're going to do, the version of the framework, the device, and the version of Python. There is an extra parameter if you choose GPU that you can specify the CUDA version. We will use region US West 2, that's where our notebooks live. TensorFlow framework, training job type, version 2.3.1, CPU device, we're actually going to use GPU, Python 3.7, and Ubuntu 18.04. And we'll use CUDA 10.2 or 10.4. I built a helper for that, so this is useful that we just specify those parameters there, and then we just build the URL with this method, and you can debug on the bottom that you're getting something that makes sense. For this, I'll just move and for the job name, we're constructing in the same way. This is overly complex, I would say, but on the tests I've been doing, it has helped me because this means automating the job name according to the hyperparameters and the setup of the machine. That way you don't have to care about that much how you name the job. Each job is already parametrically named according to the time you trained, the experiment name, the instance you use, the device type, the Python version, and the CUDA and epochs that you configured. And you can see the name at the bottom. Building a TensorFlow Estimator, I exactly don't know how to define what it is, but it's just a helper class that SageMaker contains that allows you to create a training instance to train. It allows you to also attach to that training instance to follow the training process. It also allows you to deploy a model and reserve an EC2 instance to do inference with TensorFlow serving. It also allows you to put pre-processing and post-processing functions to the model that you've deployed. A lot of helpers. In the PDF that we've attached, there is a link to the documentation, and in there you can see the entire API. What we can see here is we have an entry point that was our Python file, the row obtained from AWS, the instance count. This is in case that your algorithm can be distributed over different machines. You can put many instances and then TensorFlow will do its magic to divide or distribute the training. Instance type, that will be, for instance, ML P3X large or 2X large. Image URI, that's the Docker image URI we built before. Script mode, false. Don't remember exactly what that is for. And then hyperparameters, you have sort of freedom in this dictionary to provide multiple hyperparameters. You can create even your custom ones. And those hyperparameters will be passed as command line arguments that you have to parse on your Python script. This call here at the bottom I made just to verify that we're passing the hyperparameters. You can see the model there is always there, and we can specify in different ways, but for the purpose of this tutorial, it's not needed. Start training the job, we'll just call fit and pass the directory where the data lives. Wait false, this is if you put this to true, the notebook would actually freeze and it will start printing all the debugging logs of your script. I disabled this for the purpose of the tutorial because there is a bug or something on Keras that emits a warning on every single step of the training, and it ends up clogging the notebook if we train for many epochs. And then the job name we created before. When we have, let's say we have 10 jobs running concurrently, we can attach to any job by its job name. So we can specify in here is the variable job name because it's parameterized, but we could go and look at the jobs that are already there, the ones that are finished, that have failed, or that are in progress. We could attach to them and we directly get a vision of its history that can be also accessed through AWS console. And this is what I was mentioning before. So each of the jobs will mark as completed, failed, or in progress, or stopped, and will only charge you for the seconds that the machine was running that was on. That means when the machine is ready for you, there will be a time that you're charged for that is basically just installing dependencies of the machine, and then whatever algorithm you're running for training the model and saving. You can end it faster if you put a time limit, or if you stop your algorithm at any time. If you don't stop, it will charge you for all the time that is running when it's on. The setup time, so when you're starting, this happens everywhere. So if you're setting up a notebook, the notebook won't charge you while the machine is waking up. It will just start you charging when it's setting up the resources that you need to work on and they're on. So job name, make sure to append your name or something so you know what you're training and that is yours, because this name will also be on the S3 folder that we're saving results to. And now let's code.